In this video, we'll explore the ever-evolving landscape of space technologies and the challenges and opportunities that lie ahead. Setting the scene. With the launch of Sputnik in 1957 and the subsequent beginning of the space age, the progression of space technologies has, on the one hand, led to the development of hundreds of applications that use satellite data, including devices for everyday use, from satellite televisions to the Satnav in our cars. On the other, it has underpinned scientific progress in Earth and atmospheric sciences as well as in astronomy and astrophysics. Just to recall some of the highest public profile contributions from the field, satellite measurements showed the extent of the ozone layer depletion in the atmosphere, and the existence of exoplanets and black holes have been confirmed, among many other scientific advances. The rapid progress made in space technology led to extraordinary accomplishments for the whole human race, such as the moon landing. At the same time, these space missions have provided powerful iconic imagery for humanity, and photos like the blue marble have become universally recognized symbols of our planet and its extraordinary environment and finite resources. New space and the need for appropriate regulatory framework. Under the name of New Space, 1. There is an ongoing revolution in the space sector, with new players, commercial entrepreneurs, businesses entering a domain traditionally occupied by institutional players, old space, e.g., space agencies working with large companies to exploit the new opportunities opening in front of them. These could include new services, offered through applications of space data, from precision navigation, agriculture, surveillance, to Earth environment monitoring, etc., to more futuristic opportunities, such as space tourism or asteroid mining. Successful entrepreneurs from other sectors, from Richard Branson in the UK to Elon Musk in the US, have entered the space arena, taking risks and challenging the conservatism of the established, old space, business model. Here is where we can identify a first challenge and learn a lesson from history, preventing space from becoming a lawless, wild west, where the strongest can take an unfair advantage. This should apply to low Earth orbit (LEO), where the current regulatory framework should be further developed and enforced to manage the increasing space traffic, to prevent interferences or collisions between assets of different operators, as well as to medium (MEO) or geosynchronous Earth orbit (GEO) and interplanetary exploration and exploitation. Indeed, new regulations should be implemented respecting established treaties and principles, e.g., Outer Space Treaty, or the Convention on International Liability for Damage Caused by Space Objects. Technical challenges. Propulsion systems. Coming now to the more technical challenges, propulsion systems performance is a significant hurdle to overcome in the space sector. Starting with the launch vehicles, their capabilities, broadly speaking, payload size, and thrust, have essentially plateaued, as only relatively minor incremental progress has been made in the last decades. Indeed, materials have improved with the introduction of composites with mechanical properties far superior to the typical alloys that were used at the beginning of the space age. Design and manufacturing techniques have also improved, with progress in software simulation enabled by the extraordinary growth of computer power, or new manufacturing methods such as additive manufacturing. Guidance and control systems have also improved thanks to advances in electronics and software. However, besides the push toward green propellants, nothing substantial has changed with the solid or liquid propellants performance and related technologies, which are key to overall launcher capability. Reusable launchers are being used by a few companies in order to reduce costs or increase launch frequencies, and it is undeniable that costs have slowly come down, although this is largely due to combinations of countries' policies and market forces, but truly economic access to space is yet to be achieved. Protection of humans. Strictly related to human exploration are space health and medicine to enable humans to withstand the space environment for long periods, and the creation of artificial habitats in space and on other planets to support a reasonable quality of human life. The challenge here consists in the creation of a whole artificial environment to support people's well-being and physical and mental health, with means protecting against the negative effects of the space environment. Whether we are considering a man-made vessel for long-distance space travel or a space platform for large-scale human inhabitation or a planetary colony, some challenges overlap. These overlapping challenges include the need to create efficient closed-loop systems to replenish resources and minimize waste, with the common goal to generate an artificial ecosystem for the long-term support of human life. Near-Earth objects like asteroids or comets can pose a significant threat. Although smaller objects, such as meteors, hit our planet daily and mostly burn up whilst traveling through the atmosphere, some larger objects can survive and hit the Earth's surface with significant energy. Most of the craters produced by the larger objects that have hit Earth since its formation have been erased by the planet's geological processes, but there are dozens of large craters still visible. A great example is the 1-kilometer-wide Beringer meteor crater in Arizona, which was formed approximately 50,000 years ago by the impact of a metallic object 50 m in diameter that serve as reminders that these impacts can occur. Earth environment. Following the theme of the protection of the Earth, climate change is a significant threat to our environment with potentially disastrous consequences, and is an area where satellite technologies can help in tackling the challenge. On a global scale, satellites provide impartial information to monitor the environment and develop and validate models improving our predictive capabilities. But greater effort has to be placed in producing actionable information related to specific needs and issues, reducing the vast amount of data to simpler interpretations that can inform the political discourse. Both institutional and private Earth observation (EO) markets demand very high resolution and coverage, as well as a short revisit time, with the aim to achieve real-time Earth observation. From surveillance to disaster monitoring and management of resources, there are literally hundreds of applications, but still there is a relatively low market adoption. Low-cost space technologies. This democratization and marketization of space is evident in the growth of the CubeSat market. Here, Space HW is available at prices so low that it has attracted a growing number of customers, from space agencies to institutions like universities and schools, which in turn have enabled the creation of startups and spin-offs. However, the performance of these systems are very limited, and often the constraints come from their physical size, e.g., the size of the optics limits the resolution that can be achieved, or the size of the solar panels limits the amount of power that can be collected. This has led to the development of deployable structures to package relevant elements into small, CubeSat-compatible volumes and then deploy them in space to achieve the required level of performance. Sometimes these act as demonstrations for applications aimed at larger satellites, like drag sails. There are other technical issues that affect all smaller mass satellites, not just CubeSats, and present significant challenges, like the need to achieve high platform stability. This is crucial for all missions supporting highly accurately targeted optical payloads, e.g., high-resolution cameras, telescopes or laser communication systems, or devices that demand stability for inertial types of measurements. Large space structures. At the other end of the spectrum, with respect to CubeSats, in terms of size, are large space structures, LSS. These have been considered and studied for decades, but real progress has been slow. The capability to deploy LSS is another factor that, similarly to advances in propulsion, would enable a range of applications, but they present a series of significant challenges which depend on the specific areas. On the one hand, there are instruments like telescopes, cameras, and antennas that require large, greater than 10 meters and possibly an order of magnitude larger, high-precision reflective surfaces. Here the current methodologies, e.g., based on the deployment of precisely machined and polished mirrors whose positions and shape can be adjusted by a series of actuators, are limited by the size and number of segments that can be deployed, e.g., James Webb Space Telescope, JWST, and the overall staggering cost. In-orbit servicing and active debris removal. This brings us to the opportunities offered by robotic in-orbit servicing and the development of flexible technologies that can support multi-purpose missions. These opportunities include the servicing and potential repairing of current satellites, to active debris removal. These are not new concepts, as in 1984 the Space Shuttle Discovery mission STS-51A brought back to Earth two old satellites no longer functioning, probably the first example of active debris removal, and similarly the mission of the Shuttle Endeavour in 1993, and other following missions provided essential fixes and services to the Hubble Space Telescope. However, the opportunity here is to develop robotic technologies able to perform these type of missions at a fraction of the cost. The non-cooperative nature of the target, which could be tumbling, presents the first challenge to any approaching vehicle that has to rendezvous with this object. Don't forget to hit that subscribe button and join us on our next adventure. Until then, stay curious and keep exploring.